we on now? Okay.
Yes.
So, take 3. The last video got cut off. Then we did the rest of the video, and then realized Eliza was not filming. So I'm super happy about that. But we're back. So again, we're going to find the volume of this of a solid revolution. I hope I haven't mangled this picture too much. But we're going to take this vertical line segment. Okay, I guess I have to start from a little bit further back. Remember, we're trying to find the volume of the solid of revolution that looks like a ring. Okay, geometry can't help us, so what we're going to do is we're going to divide that solid into smaller solids, different solids for which geometry can help us. Okay, forgive me if I go quickly. Feel free to email me any questions. Okay, I'm going to try to go slowly though. So let's just look at that line segment for a second. Its width in the x direction is infinitely thin, so we call it dx. Its height in the y direction, well, I don't know how tall it is, but I know its upper bound is f of x and its lower bound is g of x. So the difference between those is the height of that line segment. So the height would be f of x minus g of x. Okay. Now, so if I wanted to spin that round, I could figure out the volume of that washer. Okay, correct? And that's essentially what we're going to do. And then what we do is we're going to stack a whole bunch of infinitely thin washers next to each other to create this solid, that ring that we've been talking about. So let's do this. Okay, I'm going to erase that for just a second. What we do is we first pretend that we're going to make, instead of a washer, an infinitely thin washer, we're going to make a disc or a cylinder. Okay, so I want you to pretend that that line segment goes all the way down to the x-axis. If I spin that line segment around the x-axis, I get a cylinder, and its volume from the last video would be pi times the radius, which is f of x, squared times the height, which is dx. Okay. That's but if you look at it, that's more volume than we want, right? We don't want that entire cylinder that created by this segment. We just want the volume of the washer created by this segment. So what we have to do, and Eliza can probably guess it, okay, we're going to take this volume and we're going to subtract away the volume created by revolving this segment around the x-axis. And you know what? I just frickin' remembered something. We were going to use the line y equals -3 as our axis of revolution.
Yeah, we know that.
Yeah, but I didn't draw it that way now, did I, Eliza? Yeah. Easy fix. Erase that. Sorry, kids. We have to make this segment come all the way down to our axis of revolution. Wonderful, wonderful. So now, this is coming, we're creating a cylinder by revolving this segment around the line y equals -3. Well, how tall is this? Well, it's the distance from f of x down to -3. So, it's f of x minus -3. But let's start with this. The volume of that cylinder would be pi times the radius squared. Now the radius, if you think about it, goes from f of x down to -3. So I take whatever's on top, f of x, minus whatever's on bottom, which is -3. So if I subtract -3, that's the same as adding.
What? Oh, +3.
Very good. Stay awake. Okay. So there's pi r squared, and then of course the width is just an infinitely thin increment in the x-axis. dx. All right, now, that's too much volume, right? I don't want the volume of that entire cylinder created by revolving this around the line y equals -3. So I'm going to carve out, I'm going to take away the volume of the cylinder created by revolving this part, okay? So I take the volume of this cylinder minus the volume of this cylinder. Is that okay, Eliza?
Yeah.
Okay. So the volume of the small cylinder then would be pi times its radius, which would be g of x plus 3. Again, that's the top boundary of that segment minus the bottom boundary of that segment times dx, and of course the radius has to be squared. So I take this volume minus this volume, I should end up with the volume of the washer created by just revolving this segment around the line y equals -3. So I'm going to do this. I'm going to say V sub washer equals pi times f of x plus 3 squared dx minus, and gosh, I hope I have room on this whiteboard, pi times g of x plus 3 squared dx. That's not the first time you've seen things have to go vertical, right? Everything going okay, Eliza?
Yeah, it's just kind of hard to see the stuff that's in the glare.
Oh, okay. Well, it's this piece right here being subtracted from this piece. Okay, so that's the volume of one washer. Okay, now, the next thing you have to think about conceptually is the way we accumulate things, like area, in math, is we integrate. Okay, so we don't just want the volume of this infinitely thin washer, we want the volume of all of the infinitely thin washers that are created by revolving line segments all the way from here over to here. Think about there's infinite number of infinitely thin line segments that start at 0 and go to the intersection point there of F and G. And each one of those line segments gets revolved around y equals -3 to create a cylinder, or sorry, not a cylinder, a washer. And then we've got to add up the volume of all those washers by integrating. Okay, let me erase this expression for V sub washer. That right there. Okay. Actually, let me adjust that. That f of x plus 3. We call that in math big R. That's the larger radius of the washer. This right here, we call that little r. That's the smaller radius of the washer. Okay. Now, that'll clean up the notation just a little bit. Big R is a function of x. I can write that as big R of x. I can write that as little r of x. Okay, but what we end up doing then is we, the volume of the washer then can be written as pi times big R squared dx minus pi times little r squared dx. And then I can, if you notice, these have some common factors in it. Both of them have pi, both of them have a dx. So I'm going to write this as pi times the quantity, big R of x squared minus little r of x.
Guys, stop it.
One more time. and then there's a dx in both of them. So essentially I factored a pi out of both of those terms, put it here, factored dx out of both of those terms and put it here. This is still v sub wash. And then to add up all of those washers, the volume of all of the washers created by little segments there, I integrate from left to right, from 0 to the intersection point. So, or from A to B, wherever the intersection points are, wherever the boundaries of the region are. So the volume would be pi as a constant, so I can pull that out of the integral. The integral from A to B.
I can see your face.
Big R squared minus little r squared times dx, and I'm going to put a box around that. That is called the washer formula. Okay, and look, I'm going to do a real example in the next video, which I probably won't put on here until tomorrow. But anyway, that's the washer formula. That's what we'll work with tomorrow. Teddy, come here.
Fight,
All right,
fight, fight.
Stop the thing. Stop the thing.